Okay, so we move to the last application using partial derivatives. We call this as a Lagrange multiplier. If we have the example, last time we have a local extrema, and then we have absolute extrema, and then now we move to the Lagrange multiplier. Is the problem is we want to optimize. You want to find the optimal value of xy that can satisfy the some conditions. Okay, you are given the functions, and that function agree with the condition given. Then how can you find the x and y value, or how can you find the point that satisfies the condition or the constraint based on the function given? So in order to solve that problem, there are many other methods actually, but we just focus on one method. We call that as the Lagrange multiplier. So multiplier is the factor that you will obtain. We call it a lambda. And then Lagrange is the name who invented that method, the name of guy, people. Okay. So for those for doing mathematics, so in future you will learn on the optimization method. Okay, so that one is more sophisticated method, right? So for the lower level, we have the Lagrange multiplier. So in this section, we are going to look at another of optimizing a function subject to given constraint. So the constraint can be more than one, but for our discussion, we only focus on the one constraint. Okay. So the objective is we want to optimize, which means that we want to find the max and the minimum value as well, the same as the previous one. But there is no constraint. So the last two, the local and the absolute, nothing to do with the constraint, no condition. But for this, we can add constraint. Okay. We want to optimize a function f subject to a constraint. So in the instruction, you must be given two functions. One is the function that you are looking for the maximum value, and subject to constraint also given by a function. So you must have a functions, and the constraint is equal to k. Okay, k here is a constant. So the constraint given, which is g here, may be the equation that describes the boundary or maybe not. It depends on the case. So the method. So f is, you have to bear in mind, f is the function that you are looking for the optimum value, and g corresponds to the constraint. So here you have to obtain the partial derivatives for both the f and the g, and you have to write down like this. So this one is a vector form. Hopefully you know how to read the vector form. So this is a vector. So the component x is fx, and then this one, the component x is gx. So in equation, what you can have is, you must be able to obtain fx is equal to lambda gx, and the second component, y component, so fy is equal to lambda gy, and the z component, lambda gz. So it is not only x, y, z component. If you have two variable function, you can have x and y only. But you have the three variable function here. You have x, y, and z, so you have three components. Okay, so not only this particular equation, you can be given by the only x and y, which is two components. Okay, so what's next? You have to write down the constraint equal to k, and just pick the g. And then at the second step, you have to plug in all the solution from the step 1 and identify the max and the min value. Okay, after you write down like this, so the objective is to obtain the lambda value. Okay, you are going to solve for lambda, you must have the value of lambda, and then from there you can find the max or the mean value of the function given. So the lambda here is called Lagrange multiplier. So if you have one constraint, so you have one multiplier, which is we call lambda, but you have two constraints, we have more than two multipliers. But in our discussion, we only focus on one constraint. Okay, look at the example 1 here. Okay, so use the method of Lagrange multiplier. Sorry, I'm not so well today. That's why you can feel that I'm just like cannot breathe properly. Okay, I'm coughing, so that's why it's not so smooth when I'm talking. Okay. So use the method of Lagrange multiplier to find the max and the mean value of the given function on the sphere. So you have a function. You want to find the max mean value of f with the condition that it is on the sphere. Okay. So this function is on the sphere. So this sphere is just like a constraint. So it's quite difficult for you to sketch because this three variable function, as we know, for three variable function, you are unable to sketch the graph. Just imagine you have a function and that function is attached to a sphere. So you want to find the max and the mean of the f which touch to the sphere. Okay. Okay. So here let's try to write down the possible information. Okay. So you are given the function x, y, z is given by x minus 2y plus 5, and then g x, y, z is given by okay, so you look at here, g equal to constant, so this one you can say that the constraint given is in terms of x squared plus y squared plus z squared equal to constant k, which is 1 to 0. So we just take this one as a g x, y, z equal to k. So now we can see that that when I draw using these apps, so whatever I wrote on my iPad doesn't appear. Okay. Alright, so from the function, this one is a constraint, so it's written like this. And in general, the constraint is written in this form: g is equal to constant, so the k is 1 to 0, and the function here is g. So we just take the g, which is ignore the k. So now your g is written to be x squared plus y squared plus z squared. Okay, so you have to write down like this. Okay, find the partial derivative for f and g. So now you can write down the fx is equal to lambda gx. So fx is 1. So you just differentiate the f respect to x, so you got only 1 here, the rest is 0, equal to lambda, and g just differentiate respect to x, so you got 2x. So you have 2x equal to 1 over lambda. Okay, so you have to write down x in terms of lambda, so 1 over 2 lambda. So that is from the x component, this one. And now we move to the second one, fy equal to lambda gy. Fy, so now differentiate f respect to y, you got minus 2, equal to lambda times gy, you got 2y. So you can have 2y equal to negative 2 over lambda, and then y is negative 1 over lambda. And then the third one, so we done the second, now we move to the third one, fz equal to lambda g z. Fz is no, z is 0. Okay, lambda gz, z is 2z. So you can have fz. I think I missed something there. fxyz, oh 5z, sorry, I missed the z here, so it should be 5. So 2z equal to 5 over lambda, so z is 5 over 2 lambda. So what's next? So remember, the aim is to obtain the value of lambda, to obtain the value of multiplier, so that you can evaluate the function later on. So how can you find the lambda? So what you are going to do now? Okay, so we have to plug in x, y, z into the constraint, okay, so that you can obtain the value of lambda. Right, so now substitute the x, y, z into the constraint function. The constraint function here, substitute that. So x squared is, you have x squared plus y squared plus z squared equal to 120, right? And then x squared will give you 1 over 4 lambda squared plus 1 over lambda squared plus 25 over 4 lambda squared equal to 120. Okay, so we want to simplify the form. We only have the equation in terms of lambda now, so we can write down that to be 1 plus 4 plus 25 over 4 lambda squared equal to 120. So you got 30 equal to 120 for lambda squared. So 30 is equal to 480 lambda squared, and we can simplify. So we can simplify this. 48 lambda squared equal to 3. Lambda squared is 3 over 48. Right. Is that correct? That's right. Okay, so we managed to get the lambda is 2 values of lambda, 1 over 4 and negative 1 over 4. Okay, and then for this particular lambda, so now when lambda is 1 over 4, so we can compute the function. So we obtain that you remember that we have the x, y, z here, this one. So you substitute the lambda you obtain, and you will get the x, y, and z. Okay, when we substitute that, so for the lambda 1 over 4, so x, y, z, that is a point. Okay, that is a point. So for x, you will have 1 over 2, 1 over 4. And then for y, negative 1 over 1 over 4. And then for z is 5 over 2, 1 over 4. So let's try to simplify. So 1 over 1 over 2, negative 4, 5 over 2 over 4. So you got 2 minus 4, 10. Right? So that is the point for the particular lambda you obtain. And then the other one is negative 1 over 4. So therefore, you can have another point. So we substitute for the x is 1 over 2, negative 1 over 4, negative 1 over negative 1 over 4, and then 5 over 2 times negative 1 over 4. And then we simplify. 1 over negative 1 over 2, 1 over 1 over 4, negative 5 over 2 over 4. So we've got minus 2, 4, and then negative 10. So we've got 2 points there that satisfy the constraint for the given function. So now you want to evaluate the value. So the last one, we evaluate the f at the point that we obtain here and here. So 4 at f at the 2 minus 4, 10. So we evaluate, and the other one, the function at negative 2, 4 minus 10. So when we substitute, you have to substitute here. So your x is 2 plus 8 plus 50 will give you 60, and the other one is minus 2 minus 8 minus 50 will give you negative 60. So obviously this is the positive 60, so this is the highest one and this is the smallest one. So you can simply say this one is the maximum value, max value, and this one is the mean value at this particular point. That's it, right? So without any sketching, you can determine the max mean that satisfy the constraint which is located on the sphere for the given function. We can determine the max and the mean without sketching using the partial derivative, which is the method called as the Lagrange multiplier. Okay, we look at the next example. So this one taken from the past year, the exam question. So use Lagrange multiplier to find the point on the cone which is closest to the point 230. Okay, you have to imagine that the problem now, you have cones, 2 cones up and down, and then you want to find out the shortest distance between the cone and the point 230. So the 230 is everywhere, not on the cone, I suppose, because when you substitute the xy, when you substitute the x and y to 3 here, you will not get z equal to 0, right? So this point is outside the cone. Okay, so in this case, the in this instruction, they don't mentioning about the max and mean. But when we look at the instruction, they have the word closest, which is the shortest, which is the small, the minimum value, right? So that is the objective. Okay, we want to find the minimum value, which is represented by the shortest distance. So that is the outcome. So meaning that that one must be to get the shortest distance, you must have the function. So that is the function f, because that is the outcome. So f should be coming from the shortest distance that mentioned here. Okay, so meaning that for the cone, it becomes the g. The cone becomes the constraint. Okay, so you have to understand, right? Because the outcome that we are looking for is the shortest distance, so you must be able to get the function f, which is representing the shortest distance. Okay, so here you have to know the formula of the shortest distance between a function and a point. So maybe a long time ago you have seen this formula before, but I'm not sure. But just to let you know, this is the general function of the shortest distance. D is the square root of the function and the point. So the point here, ABC, is the point which is 230. So I replace A is 2, B is 3, and Z is 0. Then this is the function. Okay. However, because we don't want to get messy on differentiate later, because you know you have to find the partial derivative of the D, so we don't want to have the cert, otherwise your differentiation, your partial derivative becomes more complicated. So therefore we bring the cert here to the other side, then your function is more simpler. Okay. Because whether you have the cert or without cert, at the end you have to calculate the D here. Okay, so just to make sure that we don't want to mess up the calculation, so we put the cert to the other side. So we just, when you want to apply, you want to obtain the partial derivative, you don't bother about the cert because it's already bring to the other side. Sorry. So here your function is only this. So this is your function in terms of x, y, z. Okay. And then how about g? So from the explanation there, you have z equal to x squared plus y squared. Now we're talking about the constraint. We want to develop, we want to create the g. What is the g from the information provided? So we know that the function here g is equal to k, so k can be any number, so we can have a 0 as well. So what you can do here, you just rearrange z squared minus x squared minus y squared equal to 0. So now this is your g in terms of x, y, z. So we don't bother about the value here. Okay, so now we can start to find the partial derivative for f and g. So for the first term, fx equal to lambda gx. So fx, you have to differentiate this respect to x. So you have 2x minus 2. Okay, chain rule, yeah? You have to apply chain rule, fx, that's it. And then lambda, in g, differentiate respect to x, you have negative 2x. So 2x minus 4, negative 2 lambda x. And then we may simplify 2x plus 2 lambda x equal to 4. And then we can factorize. So we have 2 plus 2 lambda equal to 4. So just like before, we want to have expression x in terms of lambda. So we have this one, 2 plus 2 lambda, we can simplify 2 over 1 plus lambda. So that is for the first component. And we go to the next, fy lambda gy. Fy, so 2y minus 3 equal to lambda. Now gy, so negative 2y. Let me simplify. So we got 2y minus 6 equal to negative 2 lambda y. 2y plus 2 lambda y equal to 6 factorize okay, y. So 2 plus 2 lambda equal to 6. Y is 6 over 2 plus 2 lambda, and we have 3 over 1 plus lambda. Okay, and then we go to the third component, fz lambda g z, fz to z equal to lambda gz is to z. To z, lambda to z. So 2z minus 2 lambda z equal to 0. Factorize the, okay, we simplify that. We have negative z minus lambda z equal to 0, right? Factorize z. So 1 minus lambda equal to 0. Okay, here we have a situation. Not this one. This one we can write down y in terms of lambda, but this one we can have the result directly. In this case, we have two possibilities, z0 or 1 minus lambda 0. But if you set z0, we cannot set z equal to 0 because the idea is the z0 is already in the point, so that is meaningless. Okay, so rather than we choose the lambda, because the aim is to get the lambda value, right? So we just pick 1 minus lambda equal to 0. So you can have lambda equal to 1. So when you have this result, then you can plug into the x and y. Then you can have here 3 over 1 plus 1, you got 3 over 2, that is 1. Okay, and then x here, 2 over 2, you got 1. So you got x1, y equal to 3 over 2, and lambda is equal to 1. So how can we know the z? Because the idea here is, first you must be able to determine the lambda, and using the lambda that you obtain, you must be able to determine the x and y. So here, based on the information that you have obtained, so you can, in order for you to obtain the z, so this there are two functions here, whether you can replace the xy in the function g or in the function f. Okay, so in this case, just like you have the lambda before this, you plug in all the x, y, z into the constraint, right? So similarly, we apply the same, because if we put here, it is still meaningless because you have no idea the d, right? Because the objective is to get the z, right? The z value based on the x, y, and lambda that you obtain. So you have no option. The option is just you have to replace the x, y into this g function so that you can obtain the z. So when you obtain the xy, the x is equal to 1, y is equal to 3 over 2, and you can have z squared equal to 1 plus 9 over 4. So you have 13 over 4. So in this case, you can have your z is plus minus square root 13 over 2. So here you got points, right? But 2 points. One is, so based on your result here, so you got 2 points when x is 1, y is 3 over 2, and your z is positive 13 over 2, and the other one is 1, 3 over 2, and you have negative 13 over 2. So you got 2 points here. Okay, 2 points that can give you the shortest distance. Okay, hopefully we can have something that after you replace this point into the D function. Okay, so now based on the points that you obtain, you got 2 points here, then you have to evaluate your shortest distance because that is your aim. Okay, find the shortest distance, the minimum value. So now we substitute into the function here, because originally we used this, so we can use that. So then you have d square. D square is so d square is the function at the point 1, 3 over 2 positive 13 over 2. So you have to evaluate that. So substitute into the formula, the function. Okay, let me copy this one, otherwise I cannot put side by side. So x is 1. So 1 minus 2 square plus 3 over 2 minus 3 square, and then 13 square. Remember, this is a d squared, not d. So you got 1 plus 3 minus 6 over 2 square, and you have 13 over 4. 1 plus 9 over 4 plus 13 over 4. So okay, so when you substitute the point that you obtain that the d square is 6.5, and then the other point, because you can see that just the z1 is negative, and then when you square that, the negative gone, so at the end you will end up you got the same value for the 2 points. So that 2 points will give you the shortest distance. That's it. Okay, remember the shortest distance is not 6.5, then you can say that the shortest distance is the square root of 6.5. That is the correct. The shortest distance d is the square root of 6.5. Okay. So you can see that example 1 and example 2 are totally different, because this one is a general one, just using a function. But the second example is really has to do with the real life problem, where you want to find the shortest distance between the cone and the point outside the cone, and then it gives you 6.5 without sketching the graph. So from now on, if the question has to do with the shortest distance, or maybe they ask for find the minimum distance, something related to distance, so that will be the function. Okay, just like you have done for this one, you have to choose the distance formula to be your function, and the other one becomes the constraint. Okay. Okay, here I have another example where this one is not in the notes, but you can have this as a part of another example. Okay, so use the method of Lagrange multiplier to find the local extremum, to find the max and min, if any. Okay, so you have x squared plus y squared plus z squared. So I think this one is just no plus sign. So z square, y square, x square, y square, z square. Subject to the constraint given, determine, and after you do the process just like you have done before, and determine whether it is max or min. Okay, so for this particular example, it is very clearly seen that f, the function, is given as x squared plus y squared plus z squared, and then the constraint is given by this one, and we just take the function on the left side. So you have 2x minus y plus 3z. Okay. Okay, so we just pick this to be g, and then we try to start to find because we have a function in 3 variables, so you have to have 3 terms here, fx, fy, and z. And then for fx, we differentiate, you got to x equal to lambda g. X is 2 into lambda, and then for x is lambda. So we just like we apply the same method. We rewrite x in terms of lambda, and then fy, so you got to y equal to lambda negative 1. So you have negative lambda, so y is negative lambda over 2. And fz, you got 2z equal to gz is 3, so you got 3 lambda, and z is 3 over 2 lambda. So based on these 3 expression, x, y, z, we put this, we substitute this into the constraint function here, the original constraint function, this one. So you replace the 2x, x is lambda, so this one lambda, minus y, so y is negative lambda over 2, so negative con, negative, so it becomes positive, and then 3z, so 3 times 3, so 9 over 2 lambda equal to negative 28, and then we simplify and we obtain for lambda. So in this case, we have only single lambda, which is minus 4. So now, just like we have before, we have to evaluate the x, y, z, the point for the lambda that we obtain. So lambda for x is minus 4, so x is minus 4. And then y here, we obtain 2. And then z, we obtain, substitute the lambda here, we obtain negative 6. Okay, so now we only have a single point. So the single point here, when you substitute into the function that we have is this one, x squared, y squared, z squared. So we have 56. Okay, so now we have obtained the local extremum. Okay, if you look at the instruction, find the local extremum, find the point that possibly we have max or min. However, since we have only a point and one value, so how can you determine it is max or min? So in this case, you have to think of the behavior of the function. So the behavior of the function tells you that this function is always increasing, right? Okay, increasing. So now the value that you obtain, 56, is the local extremum 1, meaning that you can have for any other point, there is a possibility that the value of f will be increased because whatever x, y, z that you obtain for negative or positive, and the value become larger and larger and larger. So it is not stopping at the maximum value. So there is no maximum value. Okay, there is the behavior of this function. It has no maximum because it doesn't stop. It can increase and increase again and again. But meaning that the 56 that you obtain here for this particular point is telling you it is a minimum value. Okay. So what we can conclude here, using the Lagrange multiplier, we can obtain the extremum, but based on the behavior of this function, we cannot have maximum, but we only have minimum, which is we see here is minimum. So this is something different with the previous one. Because with the previous one, you have two values, so you can easily mention that for the highest value, for the larger value it should be max and the smaller value should be min. But for this case, you have to check it out, check the behavior of the function. So that is something different. Okay. Okay, here I give you another example which related to the shortest distance, just like the previous example. So here, use Lagrange multiplier to find the minimum distance, which is the shortest distance from the plane to the origin. So here, as I mentioned before, the function is coming from the formula of the shortest distance. So the shortest distance between a variable x, y, z and the origin. So as we know, origin is 0, 0, 0. So we replace the 0, y 0 and z 0 here, and then the function is coming from the shortest distance, where d squared, this one is not d but d squared, equal to x squared, y squared, z squared. Okay, so that is the function. Now the constraint is coming from the plane equation here. So we know that just take the function, just ignore the k is 6, so we can have g here, this one. So now we start to want to get the lambda. In order to get that, we have to have the partial derivatives written like this. And then fx, you just look at the function here, differentiate with respect to x, so you have only 2x equal to lambda gx. So differentiate this one, only the left side here, with respect to x, you got 1, so that's why you have lambda 1, so you have x equal to lambda over 2. And then for the second component, fy, so differentiate this one, you got 2y equal to lambda times gy, so you got 2. So then your y is lambda. And then the third component, you have fz, so you got 2z equal to lambda gz, so you have minus 3, and you have z equal to negative 3 over 2 lambda. So to get the lambda, you have to substitute x, y, z into lambda into the constraint here. So then we obtain that the lambda is only 1, which is 6 over 7. And then we compute for the point. So since we only have 1 lambda, so you have 1 point. So we substitute the lambda into the x, y, z that you have here. This one, substitute lambda here, here, and here. And you obtain this point. Okay, and now what we want to evaluate, what is the value of the minimum distance. So we substitute the point here into the formula of distance, d squared here, as you have in f. And then we have the function using the point here is 18 over 7. But remember, the d squared is not the shortest distance. The shortest distance is d. So you have to square root the 18 over 7. And this will give you this value. Okay, so hopefully by a few examples given here, it will help you to get more understanding on the Lagrange multiplier. So I consider that we're done for the chapter 2 and we move to the chapter 3. Okay.